Okay, welcome to Integration by Parts Day 2, or the second lesson for our first technique of integration that we're going to learn. And so today we're going to discuss a couple of different things that we can do with integration by parts. The first one will be new in terms of kind of what you already know coming into it, but it is an extension to integration by parts, and it's actually a really powerful tool. It works when we have multiple iterations of integration by parts needed. So if I come into an integral and I'm going to have to do integration by parts more than once in the same problem, which is possible, we're going to figure out kind of a way around that in some situations. So we're going to talk about that, which is really nice. The second thing we're going to talk about is definite integration with integration by parts. So this is definitely more leading into your application, right? So now we're actually going to be finding a solution to a definite integral where we have to use integration by parts. How does that work? When do we actually, use the bounds that we're given? And what are my options there? And finally, the third thing, which is actually going to be in the form of a try on your own problem, we're going to use integration by parts in a familiar application, which is definitely going to be one of the ones that I shared in the first video for day 1. Okay, let's jump into it. So the first thing we talked about was what happens when we have to use integration by parts more than once in the same problem. So the third try on your own from the previous lesson, we saw that we had to use integration by substitution inside of an integration by parts problem. So it is very possible that you have to use integration by parts inside of integration by parts. However, there is one way around a particular type of function that would use integration by parts. And so it happens here. If we have some type of higher order algebraic function, so think of anything other than x to the first, right? But we want to be greater than x to the first, so like an x squared, x cubed, x to the fourth, so on and so forth. And that higher order algebraic function is multiplied or combined with some type of cyclical differential function. So sine, cosine, e to the x, those just go back and forth, or they differentiate to themselves, right? Which is e to the x. We can use a technique. It's called the tabular method, right? And we'll explain why it's the tabular method. It's really, we're going to set up 2 columns. It looks very much so like a table, and it's going to help us out. So here's my example that I want to work everything off of. And so it's the integral of x squared e to the x dx. So we notice we've got this higher order differential or higher order algebraic function, which is x squared, x to the second, multiplied by a cyclical differential function, which is e to the x. I want us to just start by imagining that we don't know the tabular method. Not that you know it yet, but you don't know it. You didn't even know it existed, or there was a different way of doing this. So imagine doing this without it. What would we do? Well, we notice it's a multiplication of 2 different types of functions, an algebraic multiplied by an exponential function. Think about your acronym LIATE. I'm definitely going to use u equals x squared as my u, and dv is equal to e to the x. That LIATE, e exponential, is at the very end, so I'm definitely not going to use e to the x as u, so I'm going to use x squared. So let's see where just see where it goes. So u equals x squared, d equals 2x dx, dv equals e to the x, and v equals e to the x. So I'll put that into my integration by parts formula, which I just listed here again just to remind us. And so u times v, I get x squared multiplied by e to the x minus the integral of v du. And so that is going to be 2x e to the x dx. Notice this second integral, right? So this guy right here. This guy right here, this second integral. That's what I was trying to do to begin with. So notice this integral right here, right? That is another integral where we have an algebraic function multiplied by an exponential function. I'm going to have to use integration by parts a second time. And so while it's not difficult, and you could do this problem like this, it's no problem. You won't get it wrong. It just might take a little bit longer. You're going to have to do a second round of integration by parts. Now, we'll finish this one. So I would then have to make a second u and a second dv. We'll call it u sub 1 and dv sub 1. U sub 1 equals 2x, dv sub 1 equals e to the x. That rule doesn't change. and then I'll do a second round of integration by parts. I want you to note, right, so we still have the original u times v, that x squared e to the x. Then I'll have to subtract another u v minus the integral of v du, right? And again, I'm trying to keep everything organized here, so I won't use u, I'll use sub 1 and dv sub 1. And so this is really u sub 1, v sub 1 minus the integral of v sub 1 du sub 1, right? This bottom integral right here. So I will have to then still do this integral, which is the integral of 2e to the x. So I notice that, okay, well, that's at least an easy integral to do. But then at the final tally, I'll have to kind of combine everything together, and you see that orange box answer. Hopefully you can follow that flow. All right. If not, pause the video and just kind of take your time with it. All right. I did want to note, right? So I've got this here. I wanted us all to note the parentheses, because the parentheses is really what makes the tabular method, I think, come together. It makes more sense that how the tabular method works if you understand the parentheses. So again, I did a second round of the integration by parts formula, which is inside of the parentheses. Therefore, I'm going to have to distribute this negative that I see right here into those parentheses. So it changes the signs of everything that's inside, right? So it will change the signs of everything there. I know that we all probably know that's what that does, because that's something you've been doing for a long time. But I want you to just take social note, because I'm going to reiterate that when we actually do the tabular method itself, right? It's going to be a reason as to why something happens. All right, so again, remember that that negative sign will change the sign of everything that's inside those parentheses. All right, so that was how we would do it if we did not know the tabular method. Let's make our lives a little bit easier. So exact same problem, but let's use the tabular method on it. Let's see how this works. So the first thing I noticed is that x squared is an algebraic function, actually derives as 0. As soon as we have that, that is a really important part. I've got an algebraic function. If I kept taking successive derivatives of x squared, it would eventually go to 0, right? And you can see that on the bottom column there under u. Right? You can see that those are all derivatives. What I'm going to do, this is how the tabular method works. I'm going to make two columns. I'm going to make one labeled u and one dv. So that's actually not much different than what we would do normally, right? And that acronym that we talked about still works. I'm still going to make that easier function equal to u. So in this case, x squared is going to be equal to u. Under the u column, I'm going to derive that algebraic function all the way down to 0. All right, and I want to go, because I can't go any further with it. Then on the right-hand side, the dv column, I'm going to integrate. Okay, so on this side, going down, right, we derived d over dx. And then on this side, going down, we took the integral. All right, so those are all derivatives to integrals. All right, let's check out the next side and see why we did that. So from there, what I'm going to do, get rid of this, is I'm going to match up every other integral with the original u and then its successive derivatives. So x squared is going to be matched up with the integral of your original dv. 2x will be matched up with the integral of your second dv, and then 2 is going to be matched up with the integral of the third dv. And I want you to really start thinking about this, like, why does this work and how does this work? Well, x squared e to the x was our original u times v when we did this without the tabular method, right? So I need to multiply u times the integral of dv, which is just v itself. So x squared e to the x. Those two need to be multiplied together, because that's the first part of the integration by parts formula. Then inside of that second integral that we did another round. And so I'm going to have another u times v. Well, this time the u is 2x, and the v would be the integral of the previous v. And so now I've got 2x times e to the x. And that would just keep happening over and over and over again until I got to the very end, right? Until there was nothing to integrate, nothing to differentiate and multiply by, which is why it's so important that this part differentiates down to 0. Okay, so start with the top of u, go to the second dv, and all I'm going to do is multiply those two pieces together all the way down. All right, I'm just going to kind of cross match them. Those are my pieces of my answer. Okay. Ignore the signs real quick and just look at, right? X squared e to the x, that's the first part. 2x e to the x, that's the second part. 2 times e to the x, there's the third part, plus c. So now the only thing I have to deal with, and remember I said note the parentheses. We have to be careful because those, when I do another round of integration by parts, I have a minus the integral of v du. So if I subtract that integral, that negative sign will distribute in and change all the signs. And so what I've done here is on top of each one of these arrows, and this would just alternate no matter how many you have, I do a little plus, minus, so on and so forth, however many you need. The reason I do this is because it reminds me that I'm going to change the sign of every single multiplication that happens once I'm done doing the multiplication. So, for instance, x squared e to the x, that's a positive function when I multiply the two, but the plus sign here says keep that sign. I'm not going to change it because that was the original multiplication you would have done anyway. The next one, 2x e to the x, that multiplication is positive, but this little minus sign says, okay, well, you're going to change that because I'm going to distribute a negative into those parentheses. So that's going to become negative 2x e to the x, which is what it's here. And then finally, there's another multiplication, 2 times e to the x. Again, that would be positive, and I'm going to keep the sign. Therefore, it is 2e to the x. Two important points. Number one, why would I alternate positive, negative, so on and so forth? Well, if you think about it, if I had to do 3 rounds of integration by parts in a singular problem instead of 2, which is our example is, but if I had to do 3, I would then have another negative that I would have to distribute in. Right? So now I've got 2 negatives that I'm distributing in. Therefore, that third sign would actually turn back to the original. Right? So negative times negative equals a positive. It's going to just reverse the sign again. And if you just kept doing it over and over again, it would just flip-flop back to the same sign, change the sign, same sign, change the sign. And so that's why we do that. The second thing I really want to note is that this negative here, this is one of the more confusing parts, doesn't mean that the middle piece or the second piece or the fourth piece or the sixth piece, whatever it might be, is always going to be negative. All it means is it changes the signs of the multiplication. So just as a hypothetical, if I said for whatever reason, I'm sorry, that's not good. Let's say this 2x was a negative 2x. I would originally multiply negative 2x times e to the x and get negative 2x e to the x. This negative that's here, again, all it says is change the sign. So the middle piece would say plus 2x e to the x instead, because I changed the sign of that multiplication. Okay. Hopefully that makes sense. Please let me know if you have questions about that. I know that can get a little bit confusing. We are going to do another example, which I think will help you out a little bit. Right? So here's my second example. Very similar, but gets the point across, which is nice. So I've got the integral of 5x squared multiplied by sine x. Algebraic function 5x squared, sine x is cyclical. Therefore, tabular method is perfect here. I know 5x squared is eventually going to differentiate down to 0. So u is equal to 5x squared. I'll differentiate that all the way down to 0. 5x squared, 10x, 10, 0. Then on the right-hand side, dv is equal to sine x. I'll do successive integrals there. Okay, sorry again, just had to fix something really quickly. So on the right-hand side, dv equals sine x. I'll do integrals the whole way down. So the integral of sine is negative cosine, and then it just flows through. So now it's about putting the pieces together. So I know that I'm going to multiply 5x squared by the integral of sine x. So I get 5x squared multiplied by negative cosine x. So that multiplication is negative 5x squared cosine of x. Again, this plus sign here does not say change that to a positive 5x squared negative cosine x. Or sorry, positive 5x squared cosine x. It just says keep the sign of the original multiplication. That's why this first part of the answer is still negative. And then I move down to the second part, 10x multiplied by negative sine x. That would be a negative 10x sine x, but this negative sign says change the sign. So originally negative, changing the sign to a positive 10x sine x. And then finally, 10 times cosine of x. Well, that says keep the sign, which is positive to begin with, so I'm going to keep it positive. And then, so once I can't do anything with 0, because 0 multiplied by anything would go away, so I'm done. Okay, and there's my answer. All right, very good. Again, remember, if I pause the video, it's because I probably just caught like a small mistake in my work, and I'm just fixing it. And hopefully I explained it well enough there. Just stay patient with me with that. It's I'm certainly not perfect, but I usually catch my mistakes pretty quickly. Okay. So that was the tabular method. Hopefully that made sense, and hopefully you have a fair handle on it. You'll do some practice, and I'll help you out as much as I can moving forward with it as well. Okay. The next part is using by parts, but with definite integration. And so really, you've got two different options here, because this gets a little bit funky because once you use the integration by parts formula, you've got that UV hanging out in front, and that part's already, for lack of a better word, it's already done. You're not integrating it any further. So you could evaluate that before you do the second part of the integral. But I actually recommend to just wait until the very end. All right. And that's actually how I'm going to show it to you. So just do everything at the very end. You'll only have to do one f of b minus f of a to really compute that definite integral, as opposed to trying to keep, in your head, oh, did I do that first part first? Or do I still need to compute that part at the very end? Or what's going on? I just, for your sake, I think it's easier just to do everything at the very end. All right, so let's take a look at this example. I've got the definite integral from 0 to 1 of x e to the x. All right, so now I'm actually finding the area underneath of this curve. Okay, so this is a true application of integrals. So I've got the function x e to the x, it's some curve. I'm going to find the area underneath of it from 0 to 1. And so I'll do my integration by parts. Hopefully by now we recognize u is going to be equal to x, take its derivative, dv is equal to e to the x, I'll take its integral, and we'll plug it in. All right, so now I'm up here to this part. And again, this is the correct notation, just to kind of keep things together. That first part, that u times v, x e to the x, it's already been integrated, right? That's already finished. So I could technically evaluate x e to the x from 0 to 1 with f of b minus f of a, f of 1 minus f of 0, and just kind of leave that to the side, and then do a separate definite integral, which is from 0 to 1 of e to the x. But then I would have to evaluate that integral and then combine those two parts together. So this is where I think it's actually easier just to finish with integration by parts, then evaluate it at the end. So x e to the x minus the integral of e to the x, which is just e to the x itself. I'll just leave it here, and now I can just do one final computation, f of 1 minus f of 0. And if you see the math there, we get e minus e, which is 0, minus 0 times e to the 0, which is 0, minus e to the 0, which is 1. So minus a negative 1 becomes a positive 1, and I've got my answer. All right, hopefully that made sense. We're going to move forward here. Let's do a try on your own. So at this point, I want you to pause the video based off of that last example. I want you to try this one on your own, okay? The beginning of this is more just integration by parts practice, right? So how would you integrate 2x sine of 2x? And then at the very end, I want you to use definite integration to find an actual value. All right, this time we're going from pi over 4 to pi. Give it a shot. Okay, welcome back. So the first part is really just setting up integration by parts, right? So we're going to get rid of here. Hopefully we saw that u is equal to 2x. That's your algebraic function, and sine of 2x is your trigonometric function. So 2 dx. Note here, right, that we have to use integration by substitution in order to take the integral of sine of 2x. So in that case, I would make u equal to 2x, and I would eventually get negative cosine of 2x over 2. Right? Hopefully you see that integral. That's done by integration by substitution, right, or u substitution. Pause the video, make a note there if you don't get that part, just because we can take care of that. It doesn't necessarily ruin the flow of the problem, but if you need help with how we got from dv to v, please note that. All right, but for right now, trust that that is the answer. All right, so let's look here. So here's the part where I've got u times v. So that should be, I'm sorry, that's right, negative x cosine of 2x, right? So I've taken v, multiplied it by u, so 2 over 2 would cancel to 1 or simplify to 1. So negative x cosine of 2x minus the integral of v du. All right, so v is cosine of 2x over 2, du is 2 dx. So again, the 2's would simplify with one another, and I would have to integrate this piece right here. Wait until the end to do the definite integration piece. You're really just working with integration by parts at this point. So negative x cosine 2x would stay, and then I would do the integral of cosine of 2x. Again, that's another u substitution where u would be equal to 2x again. And that's why you've got that divided by 2 piece. All right, so just remember that. And so once I integrate there, we get positive sine of 2x over 2. This looks very similar to something you would have done last year. You've got f of pi minus f of pi over 4. And I'm going to plug in pi, subtract when I plug in pi over 4. You can stop the video again right here if you want to do some of this trigonometry, some of this unit circle work, which you'll absolutely need to know. But once you do that, you should get negative pi plus 0 minus 0 plus 1/2, which should be negative pi minus 1/2. And that's a good enough answer for us there. Okay. Okay, the second try on your own. Give it a shot. From 0 to 2 of x to the third, the integral from 0 to 2 of x to the third e to the 2x. Go for it. All right, let's see if you caught what to do. So hopefully you noticed that it's an algebraic function that derives to 0 multiplied by a cyclical differential function. So I am going to set up integration by parts here. And then at the very end, I'm just going to do a definite integral computation. So I'll set up my integration by parts. X to the third goes, I've got 4 different pieces here. And so I'm going to have to do 4 different integrals of e to the 2x. Again, that integral is a u substitution where u is equal to 2x. And so each time I'm going to have to divide by 2, which is why you see this denominator jump up from 2 to 4, 4 to 8, 8 to 16. But e to the 2x stays the same. So I have to put all these pieces together. The good news is that all of the integrals of e to the 2x are positive. So I am just going to follow the sign chart all the way down, and that's going to be the signs that are in between. So that set up x to the third multiplied by e to the 2x over 2. And then all the way through, you can see these multiplications put together. Again, if you need to pause the video, please do that just to see how those pieces fit. I'm going to evaluate that from 0 to 2. So I'll do f of 2 minus f of 0. That's what that should look like. The f of 0 is really nice because most things completely zero out except for the very last piece because there is no just multiplied by x. I have an e to the 0, which I know will be 1. And you'll have to do some fractional work here to combine some things. But once you do that fractional work, here is your final answer. So easy integral, a little bit of work at the very end with combining some fractions and working with e's and things of that sort. But again, pause the video, try it yourself. If you still don't get it, make a note, let me know. But really try to do that because that's something I think we're all capable of doing. It's just finding some common denominators and combining fractions. All right, last try on your own. The region bounded by the function f of x equals 2 times the square root of x sine x and the x-axis on the domain of 0 to pi is rotated about the x-axis to form a solid figure. I want you to find the volume of that figure. So this is one of our applications, I said, right? So this is a volume of solids application. This is something we definitely need to know throughout the course. If you want, I recommend getting your calculator, typing in f of x equals 2 square root of x sine x if you want to see that region, see how it's bounded, what it looks like, but only on the domain from 0 to pi. If you rotated that region about the x-axis to form a solid figure, how would you find the volume of it? Pause the video, give it a shot, come back. All right, let's take a look. So very first thing I need to start with, and hopefully you know this, right? The volume, this is a disk method problem, is going to be equal to pi from the domain of 0 to pi of f of x squared, right? That's your pi r squared. That's finding the areas of your small circles multiplied by dx, which gives those circles a little tiny bit of width, all right, or depth rather, and that's what makes it a solid figure. So I'm going to be adding a bunch of little volumes together to get a full volume at the very end. So I know that my function is 2 times the square root of x sine x. This actually works out really nicely because I'm going to be squaring the square root. So I'll square that whole thing, right? So the 2 gets squared as well. And so I do get that is equal to the integral of pi from 0 to pi. Pi times the integral from 0 to pi of 4x sine x dx. At this point, I'm sort of right back to one of the other try on your own problems. I just have to do integration by parts and then use the definite integral at the very end. So I'll make u equal to 4x and dv equal to sine x. You follow that. And then I'm just going to unveil this whole thing here, right? So in the very end, the volume is going to equal to pi. So this is the part I wanted to point out, right? So that pi is this same one that's out here. So I'll have to keep that on the very outside. And then on the inside is your u times v minus your integral of v times u, or du, v times du. Flow through that integration process. It's not too bad because the integral of negative 4 cosine x is nice and easy. I do have that negative multiplied by negative, so that's why you see a positive 4 sine x at the very end there. I'll do f of pi minus f of 0. Again, the 0 and the pi in this situation really help me because cosine of pi is negative 1, sine of pi is 0, and then sort of vice versa for zeros. Cosine of 0 is 1, and sine of 0 is 0. Plug all those pieces in together, and here's what we get, right? So here's your f of b, and here's your f of a. All right, so f of pi minus f of 0. I still have that original pi that's out in front. Okay, and then you finally get 4 pi squared from that. All right, hopefully you were able to follow along. Again, make notes, pause the video, look at the work done, try and do it yourself again if you have to, and let me know what questions you have. All right, homework will be posted on my Malvern. Please use my Malvern submission and let me know if you have any troubles. All right, thanks guys, have a great day, and I'll talk to you soon.